Right, so that brings us to Greenberg's theorem, having all those definitions out of the way. Now, Greenberg's theorem states that if you have a plane graph that's Hamiltonian, and it has a Hamiltonian cycle C, then this sum is always equal to 0. Now, this is not difficult to prove, but it's a very useful result in proving that some relatively complicated graphs are not planar. So how the proof works is basically you distinguish, okay, so let's say the number of chords that lie interior to C is denoted by this quantity C, and all the regions within the cycle C adds the number of regions C plus 1, because you can see this clearly. If you have your Hamiltonian cycle there and you have your chords, those chords always partition the interior of the cycle. If there are C such chords, you're going to have C plus 1 regions. So there's just a nice illustration. There you've got 3 chords, and they partition that whole cycle into 3 into C plus 1, which in this case is 4 regions. Okay, so if you go and sum over all the regions, you go and count the number of interior regions. That all adds up to C plus 1, and from that you can solve the number of chords, which is the sum of you counting all the regions and you subtracting 1 from that. Then what you're going to do is you're going to sum over all the edges interior to the Hamiltonian cycle C, and you let that quantity be n. So n denotes the result obtained by summing over all regions interior to C, the number of edges on the boundary of each such region, like we did previously with all the polyhedra and all of that. Then each edge on C is counted once, obviously, and each one of the chords is counted twice, because each chord is on the boundary of 2 regions. So that n is going to basically be the same as here you sum over all the edges, okay? And so what you're going to count is you're going to count n edges, the edges lying on the on that Hamiltonian cycle, and then you're going to count the chords inside of the cycle, and that's going to add up to 2C. Right, so therefore this summation, you just do all the substitution that you previously, we know what the value C is, we do that substitution, and then you solve for the quantity n minus 2. Okay, now you can have a symmetrical argument for all the chords that lie exterior on the exterior of the cycle C, and you can find a exact same expression in terms of Ri prime, and you're going to also get that's equal to n minus 2, and then equating the two things and regrouping the terms on the left, you see that that adds up to 0. So it's not a terribly difficult proof, but it's a nice little result to show that certain graphs are not Hamiltonian. And that brings us to the Tat graph. We're going to quickly prove that the Tat graph is not Hamiltonian. So there's the Tat graph in all its glory, and we are going to prove that this graph is not Hamiltonian. Now that would be a very difficult thing to do if we had to do that by case analysis. It would be almost impossible. You would have computers run for days on end to actually try and prove this. But we can actually do it quite easily with Greenberg's theorem. Right, we're going to assume, to the contrary, that the Tat graph is Hamiltonian. So by Greenberg's theorem, we have this summation, that summation we talked about is equal to 0. So then G has got a Hamiltonian cycle C, and here they say necessarily C must contain exactly 2 of the 3 edges, which we will define just now, E, F1 and F2. Say F1 and either E or F2. So if you go back here, the Hamiltonian cycle must contain that edge, or either this edge or that edge. Now, why must it contain exactly two of these highlighted edges? So why, okay, so we check the case. Can it contain three of those edges? Yes or no? Or can it contain only one of those edges? Okay, what happens if it contains three of those edges? Right, so the path can go through here and it can go there, and then it has to go through here again, and then go through there, right? And then it has to go through there and somehow get back there, but that's not allowable. We can't have that. Or it could go through here, then go through there, go through there, go through there, and then again back. That can't happen. Okay, that can't happen. Or it could go through here, and then go through there, and then come back here and go through there. Again, that cannot happen. Okay, so it cannot contain, the other possibility obviously is it could go through here and then go through there, but eventually it's going to have to come back there and then pass that part there again. One can go through all those possibilities, and you can clearly see that it cannot contain three of those edges. Can it contain one? It contains that one. It could go through there and then forced to go through there. So that can't happen. If it goes here, it's going to be forced to go through there. Right, if it goes through here, it's either forced to go through, it might go there, and then come here again, and then it's going to go through there. Okay, so that can also not happen. One can also go and look at all the possibilities. Goes through there. It either is going to go there, or it's going to go through here, and then it's forced to go through there. So again, you can also look at where it only contains that edge. There again, it's going to have to come through there eventually, either that one or that one. So therefore, it contains exactly two of those edges. Okay, now we can have a symmetric argument. This graph is nice and symmetrical. So if we look at by the same argument, you have that two of these three edges must be contained in this Hamiltonian cycle by the same argument. Right, so this means that either we have this edge contain this edge, or it contains that edge. And without loss of generality, we can therefore assume that it must contain F2 as well. And therefore, we can assume that E is definitely, which is that edge, is definitely not on the Hamiltonian cycle, because we said that the Hamiltonian cycle can only contain two of those edges. Right, so what we now do is we take G1, and we say G1 is the component of G that you get by deleting the edges E, F1, and F2. And this component G1 must contain W. Right, so the component we're talking about is this whole component here. Right, so G1 must contain a Hamiltonian V1, V2 path P prime. Alright, this is obvious because we're going to come through here. We have to include all the vertices there. We can't come back again. So this path has to contain that runs from V1 to V2 through this component. It absolutely has to contain all those vertices. So there's a Hamiltonian V1, V2 path through this component. And so we can go and join V1 and V2, form a new section, this component here. and that is going to be a graph that has a Hamiltonian cycle, and it's planar. So there is G2, which is G1 plus that edge, and that is a Hamiltonian graph that contains a Hamiltonian cycle C prime, and that consists of the path P prime. Now, applying Greensburg's theorem, we then get that this summation for this special graph G2 holds. There are only R3, R4, R5, and R8 regions. Right, so that, as an example, is an R5 region. That's an R3 region, okay? There's an R4 region. And then we've got a 1, 2, 3, 4, 5, 6, 7, 8. We've got an R8 as well. Okay, so there is my R8. Okay, so writing down that sum, we have to just make a few observations. Alright, so let's look at this R3 region here. Okay, that R3 region, is it an interior region or an exterior? We're only looking at G2 now, which again is that whole section there. So is that interior or exterior? Right, now we know this edge does lie on the cycle. Right, so we could, this Hamiltonian cycle could go like that, and in that case, this region here is an interior region. Okay, now this Hamiltonian cycle can't go like that, so the only other option is for it to go like that. Okay, then what happens in that case there? If it goes like that, then it has to get back there and go there or there, and that is a problem there, because then we are going to repeat a vertex in the cycle, which is impossible. So the only other option is for it to go that way, and that is the only possibility. So this region is an interior region. So R3 R3 is 1. Okay, so R3 minus R3 prime is 1 minus 0, which is 1. And what about R8? So there again you have that situation that holds there, and so you have to have this whole like Hamiltonian path that goes that way there. And so R8 must lie outside of this Hamiltonian cycle. So that gives me this R8 minus R8 prime equals to minus 1. So plugging that back in, we get this expression here. And so we have this necessarily both W and W1 and W and W2, which are these two little edges there. Both of them obviously must be on this Hamiltonian cycle, because W has degree 2 in G2. Okay, so we've got these. You've got those two edges there. Now, if you have that situation there, and you have such a situation, then eventually the path has to come back to include that vertex there, and then it either has to go there or there, which is definitely not going to happen. So you have to have that, and that is going to go all and include all the vertices there. So that implies that that region there, which is an R4 region, is definitely in the interior region of this Hamiltonian cycle. Okay, what happens if you have that situation there? Again, you can't have that, so you must have that. Okay, and then again, that is a region that is that's an R4 region that is interior to this Hamiltonian cycle. So again, you cannot have that situation. So the implication of that is that R4 is at least 1. All right, so that R4 is at least 1. The only other R4 region is this region here. So therefore, you could have one of two possibilities. Either the difference between R4 and R4 prime is 0, or the difference between R4 and R4 prime is 2. Then you've got the two cases. If R4 minus R4 prime is 0, that falls away. And so basically you've got an integer times an integer is equal to 5, but that's definitely not possible. So there we go, get a problem. Or you could get the other situation where R4 minus R4 prime is 2, and in that case 3 times that is 1, and R5 minus R5 prime must be an integer, and that certainly is definitely not possible. So therefore my graph, my Tat graph is definitely not Hamiltonian. Alright, so that concludes the section on planar graphs.